Okay, here we're supposed to write the third degree Taylor polynomial for f around x equals 2 and use it to approximate 1.5. So they gave us a series of derivatives, the actual function at 2 and then the first, second, and third derivatives. You have to keep in mind that each term of a Taylor polynomial is not just the nth derivative, but also x minus a, which is in this case 2, to the n, over n factorial. And that's where most people make the mistake, is they just look at the derivative and think they're good. So the first term is this constant term, it's negative 3. Second term will be the first derivative times x minus 2 to the first over 1 factorial. The second degree term will be the second derivative 3 times x minus 2 squared over 2 factorial. The final term, we have negative 8 as our derivative, x minus 3 cubed over 3 factorial. And then using that to approximate x equals 1.5, you would actually have to do on your calculator. They were allowing calculators for this, so I'll let you work that out on your own. So then they're saying, I like this problem because it gives you this terminology, which is the Lagrange form of the error. They're basically saying that the fourth derivative, they're telling you that the fourth derivative is less than or equal to 3 for all values on the interval from 1.5 to 2. I just realized that should have said 2 there. 2 is our center for all the problems. Okay, so back to part B. They're giving you the maximum value of the derivative. And remember that for the Lagrange form of the error, that the error for the nth degree is less than or equal to the n plus 1 derivative times x minus the center to the n plus 1 all over n plus 1 factorial. So if this is the fourth derivative, then basically they're going to ask you to find the third degree error. So it's the third degree error. R sub 3 is less than or equal to the maximum value of the fourth derivative, which they told us is 3, times x minus 2 to the fourth over 4 factorial. And the only question is, what do we plug in for x? Well, they gave us this interval of 1.5 to 2. So we are going to plug in 1.5 in order to maximize the value of x minus 2 to the fourth. And when you work this out, you're going to get a decimal approximation. And I'm going to go check and come back. Okay, your decimal approximation is approximately 0.0078. So explain why f of 1.5 cannot be negative 5. Well, that actually leads from the number that we got as our approximation here, which I'm going to go check and come back. That approximation was negative 4.958. So you guys know that the Lagrange error bound means I basically add or subtract this error to our approximation to get the interval of values that we could possibly be on. So if I added, say, 0.008 to this number, or even, I guess, if I subtracted 0.008, I would get out the following, negative 4.966, which is still not even negative 5. So the point is that negative 5 is not within the Lagrange error bound. If we take our estimate and we add or subtract this error bound, the number negative 5 will not be included. So the next part of the problem is that they want us to write a fourth degree polynomial around for g of f of x squared plus 2. What that does is it's a left shift by 2. So it takes u being centered at 2 and it's going to end up with u being centered at the origin. So the fourth degree polynomial, what you want to do is take the values that you got for part A, which was the third degree Taylor. So we're going to write them down, negative 3 plus 5, let's see if I can get this, negative 3 plus 5 times x minus 2, and I need one more term, and that term is 3 times x minus 2 squared over 2 factorial. So plus 3 times x minus 2 squared over 2 factorial. Take this and plug x squared plus 2 in for each of the x values. And then you're going to see why I only needed to get through the squared term. So I have negative 3 plus 5, and then x squared plus 2 minus 2, plus 3 times x squared plus 2 minus 2 squared over 2 factorial. And then what you see is the plus 2 minus 2 goes away. And when this simplifies, I get negative 3 plus 5x squared plus 3x to the fourth over 2 factorial. That gives us our fourth degree. Then it says, use P to explain why we must have a relative minimum at x equals 0. The only way to do that is actually to use the second derivative test. We cannot use the first derivative test with series because we don't have the actual functions. We only know that we can match up at x equals 0. We don't know what the interval of convergence is. So we don't know what's happening to the left and to the right of 0, which would be required for the first derivative test. So if I were to take the second derivative of this expression, only this middle term with the squared would matter. If I take the first derivative of it, I get to 10x, and then the second derivative is just 10. So the second derivative of g at 0 equals 10, which is positive. So that means my function is concave up, and I must have a local min.